In this video, I'm going to show how we can calculate half-life using equations. That means we can use non-integer values of half-life, and this is part of topic 12.2 in higher level IB physics. Take a moment and read the success criteria that I hope you will be able to answer after watching this video. Okay, so I'm already hoping that you realize that the rate of decay is based on a random process. I've done it in some other videos. The other thing I want you to realize and remember is that the rate of the decay was dependent on how many nuclei we have. If you have more nuclei, I should hear with a Geiger counter tick, 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 tick more often than if I have less, even if it's the same material, because there are more nuclei, so there's more probability that we will have nuclear decay. So if I take a look at this equation right here, let me talk to you like a math teacher for a moment. This n by dt is saying the rate of change of the number of nuclei, dn by dt, the rate of change of the number of nuclei is proportional to the number of nuclei. What I just said, but in math terms. And that negative sign there is because we have a exponential decay. So if I go from having proportionality to have an equal sign, I need to put in a constant. So now I have the rate of decay of the number of nuclei will equal the decay constant times the number of nuclei. Now, one of the things with IB physics is we don't do it with calculus, so then I have to give you the solution to this equation, and here it is. If you've done differential equations already in your math class, you'll see I don't have a plus c here, but that's okay because I've got some actual values in here. So the number of nuclei after any given time is going to equal to n naught, which is the original number of nuclei, and then the exponential of the negative of, there's our decay constant, times the time. Okay, so I've got that extra constant in there. We call it the decay constant, and it's the probability of a decay of a nucleus per unit time. We're going to talk about later how it relates to the half-life that you should already know about. Now, this part here is clipped from our data booklet. Anyone who knows me knows I love that data booklet. All the things that's not worth memorizing is in the data booklet. Now we have this letter A. We've talked about the activity being the number of radioactive disintegrations per unit time, and we know that it's proportional to the number of nuclei. I could make a very similar equation like I did before, where I have the activity, and this would be the activity naught, which would be at time equals 0, e to the power negative lambda t. Now, if you look in the data booklet, it says that this is lambda n naught. And so here's where I want to point out a really important equation that's not in the data booklet that you almost think should be. A equals lambda n. That is the relationship between the activity is equal to our decay constant times the number of nuclei. Now, if I want to know it at any given point in time, like for example, if I want to know it at time 0, then I would say A naught equals lambda n naught. Or I could put it later at any point and use it as well. Now, it's not in our data booklet, but if you look carefully, you can see that it really is there. Because this technically should be A naught. And instead, I've got lambda n naught. So that shows you right there that A equals lambda n. The activity equals the decay constant times the number of nuclei. Now, I just want to take a moment and talk about this equation because it's listed in our data booklet very close to the others, but it's not actually about radioactive decay, but it is about nuclear physics. What we have is this thing called the Fermi radius. Now, the density of the nucleus is fairly constant no matter which nuclei we're looking at. And so because they have a constant density, then if I know how many nucleons, I can use this equation here to approximate what the radius of the nuclei will be. So this R stands for the radius of the nucleus will equal R naught, that is the Fermi radius, and A to the power 1. Now this A is not the activity, not the A that's listed down below, and that's why I wanted to point it out here. This A is from the nuclide notation. When you write it like this A is actually the nucleon number. Okay, slight derivation, but it's still part of 12.2. So now let's use this equation in a little bit more detail. How do we find this decay constant here? And what are some ways we might have to be able to calculate it besides just putting some numbers into an equation? So let's think about this first. I'm going to talk to you like a math teacher for a while. Let's take the natural logarithm of both sides. Now, if you remember from math class, when you have natural logarithms of two numbers multiplied together, you can then take and separate them by being, in this case, ln and naught times ln e to the power negative lambda t. Now I've also taken another little shortcut. Once I have ln e to the exponent minus lambda t, that lambda t can come down in front. Now, if I just go and clean this up a little more, because ln e equals 1, I get this equation. Now this is it might stand out for us in a way because I've got now a full linear equation. Here's one variable and here's the other. And now that I don't have any exponents and I don't have any powers or things like that, if I put the value ln n on my y-axis and I have t on my x-axis, I'm going to get a linear equation. I'll get a straight line. Y equals mx, and here's my b. So take a look. I have a straight line. If I get the gradient of that line, it will be my decay constant. And this value right here, my y-intercept, will be ln of n naught. Now, why would I like this from a graph rather than just putting in some values of a point? Well, we know that every measurement we take has some error. So if I could take and I could make a line of best fit with my values and do the gradient of that, it's like taking a weighted average of all my values, and I'm going to get a better, more accurate answer. Now, one of the things we also have to pay attention to is, in one hand, we can calculate the values of natural logarithm of the number of nuclei and graph it like I was talking about in the previous slide. But we didn't always have super fast calculators to do that for us. So what we've got here is something called log graph paper. With the current coronavirus and looking at numbers, people are getting better at looking at logarithmic graphs. But let me just point this out. If I have the value 1 here, 2, 3, and I go all the way up to 10. Now 20, 30, all the way up to 100, 200, 300, and so forth. I'm just getting lazy and not writing in all the numbers. What this would do is I wouldn't actually have to calculate ln n and then graph that value. I could just plot the actual values I have, whether it be, 3. Sorry, let's start up here with, let's say I had 300, and then I had 150, which will be in here somewhere, and then I would have 75, would be in here somewhere. I am going kind of quickly here, so if I don't have it exactly right, don't get upset. And I'm going to be around 32, and then I'll have 16. And you can see that these numbers that I'm doing are giving me a pretty straight line, and I didn't have to calculate the ln value of them. This is important here in our topic 12.2. It will also come up, this idea of being able to use graph paper, log graph paper in 11.3 when we do capacitors as well. So now that we've been talking about this new thing called the decay constant, we want to get a relationship between it and our half-life. So let's take some numbers and we're going to plug it back into our equation that we've been using. First of all, if I want half-life, then that means it's going to be n naught divided by 2. And at that time, I'm going to use the symbol t with a subscript 1/2. Okay, so let's start by putting the values in. And we can cancel out these n naughts. And let's go and take the natural logarithms of both sides. Remember, we're looking for something that's in the exponent of the e there. Now, when I do that, I'm going to get ln 1/2. And on the other side, remember, ln e to the exponent, we bring down the exponent, and ln e is just 1. So this is what I'm left with. Ln 1/2 equals negative the decay constant times the half-life. But we can make this a little easier to read. If I move that negative sign to the other side, I get negative ln 1/2, which will be just the same as ln 2. And isolating for the half-life, we get the half-life is ln 2 over the decay constant. Now this equation is not in our data booklet. I know, makes you sad. But sometimes in a question, you can use it. As long as the question isn't asking you to derive it, you can remember this equation and use it. But pay attention. If it is 3 marks, then you're not going to get 3 marks for just writing that value down. You're going to have to show where it comes from. Now, there are 2 examples where it's not very easy to measure the half-life, so we have to be a little bit more creative. The first case is if there's a long half-life. So if that was the case, then it's not very easy for us to measure over time because we really won't get a change in our activity rate. So what we have to do then is go back to that equation I referred to earlier. The activity equals the negative decay constant times the number of nuclei. So if I have a fairly constant activity, and I could calculate N, and I could do that with some chemistry, right? I'll have the mass of the material. I can calculate how many moles and then how many nuclei must be inside with Avogadro's number, and thus I can calculate my decay constant. Once I have a decay constant, I can put that into the equation we just derived, and ln 2 divided by the decay constant will give me my half-life. Now, there are some things that do have a very long half-life, such as the waste from creating nuclear energy. There are times where it's a good thing. For example, the long half-life of the alpha emitter in smoke detectors is fairly constant. So then, if the current that's being created from it changes, i.e. smoke is in the way, then it sets off the secondary alarm, and it's very useful when the fire alarm goes off. So there's not necessarily saying, hey, long half-lives are necessarily all a negative consequence. So you probably guessed then we also need to talk about what happens if something has a very short half-life. If you look on a periodic table, you might see that some of them have a half-life of microseconds. So how on earth did someone see that or be able to measure that? One of the characteristics of radiation is that it can cause ionization. Remember, knocking an electron out of an atom, causing it to create an ion. Well, if that's the case, then I have an ion and I can conduct electricity. So if I then can measure this, I could display it on an oscilloscope, and then really the only thing holding me back is how accurate and how short of a response time does my oscilloscope have, and that's how I can measure things even down to microseconds. Okay, so take a moment and read through the success criteria again. Hopefully this video has answered these for you and you can say yes to all three of these statements.